Hi, welcome to this lesson on number patterns, infinite geometric series. Let's have a look at question 4 on solving infinite geometric series problems. We're given that a geometric sequence with all positive terms, that's probably really important, has a convergent infinite sum of 25 over 2. The sum of the first two terms is 12. Find the value of a, the first term, and r, the constant ratio. So first of all, we know it's a geometric sequence. T sub n, a times r to the n minus 1, where n is a natural number. We are told that all the terms are positive. So when we list out this sequence here, they should all be positive numbers. So that's pretty important. And we know that it has a convergent infinite sum. So that tells me two things. Firstly, because it's convergent, right, that tells me two things. My r value, whatever it is between 1 and minus 1. Okay, so when I work it out, it has to be between there because of the convergence. I also know that the S infinity, which is a over 1 minus r, they told us that that infinite sum is 25 over 2. So that's two pieces of really important information here. So therefore, I'm going to call this equation 1. Lastly, we were told that the sum of the first two terms, t1 plus t2, that is 12. But I'm going to rewrite t1 as a and t2 as a times r. That's 12. I'm going to call that equation 2. So why did I do that? I now have a system of simultaneous equations with just a and r as the two variables, and I've got two equations, therefore I can solve for a and r. So let's do this. From equation 1, I'm going to multiply both sides by 1 minus r. That would cancel out the denominator here. And on the right hand side, it'll be 25 over 2 times 1 minus r. So let's substitute this into equation 2. Equation 2, firstly, what I'm going to do is I'm going to pull out a factor of a. I'm going to be smart with my algebra here. So it's going to be 1 plus r equals 12. But I know what a is. It's that value here that we just made here. So therefore, a is going to be 25 over 2 times 1 minus r. That's my a. Times the 1 plus r equals 12. So now I've only got r's here. Therefore, I can now solve this quite nicely. To get rid of this 25 over 2, I'm going to first multiply both sides by 2. So that'll give me 24. And then I'm going to divide both sides by 25. So on the left-hand side, this is actually the difference of two squares. So if I factorize that out, that'll become 1 minus r squared. If I distribute it out rather. And that's equal to 24 over 25. Now I'm going to bring the r squared over to the right-hand side. So I'm going to get 1 equals r squared plus 24 over 25. And then I'm lastly going to subtract 24 over 25 on both sides. So 1 minus 24 over 25. 1 is 25 over 25. So I'm left with 1 over 25. Because 1 is 25 over 25. So therefore I have the equation r squared equals 1 over 25. Because I'm solving this quadratic equation with r as my expression squared, if I square root both sides, it's going to be plus or minus the square root of 1 over 25. But that's going to be plus minus the square root of 1 over the square root of 25, which is plus or minus 1 over 5. So those are the two possible r values. 1/5 or negative 1/5. Now, if I look very closely on a number line, the radius, I keep saying radius of convergence, but that's actually a very common term in mathematics. But basically, the interval of convergence between negative 1 and 1, 1/5 is over here. Negative 1/5 is over here. So both values are within the interval of convergence. But how do we know if both are correct? Well, let's substitute those two values of r into our sequence and see which r will make sense. Because the only piece of information we haven't used yet is that the sequence has only positive terms. So I suspect that one of these r values is going to give us an alternating sequence of positive and negative terms. That's the one that we have to discard. So I'm going to make some room here and just rewrite what we have. So what did we find? We found that r is either 1/5 or negative 1/5. Let's have a look at when r is 1/5. So recall that your sequence Tn is a times r to the n minus 1. We didn't find a yet, but we can now. From that equation number, let's call it equation 2 that we worked out, it was a plus ar equals 12. I'm going to plug in r equals 1/5 here. So first I'm going to factor out and then rewrite that equation. So a times 1 plus r equals 12. So therefore a into 1 plus 1/5 equals 12. 1 plus 1/5, 1 is 5/5. So that becomes a times 6/5 equals 12. So therefore a equals, so to get rid of 6/5, I multiply by 5, then I divide by 6. 6 goes into 12 2 times, so I get a equals 10. So the sequence looks like this. The first term a is 10, and then I keep multiplying by 1/5. So the next term will be 2, then 2/5, then 2/25, and so on. So let's have a look at this. First of all, it's a geometric sequence. Yes, a is 10 and r is 1/5. All positive terms. Yes, every single term is positive. The sum of the first two terms is 12. 10 plus 2, that's 12. This satisfies all the conditions. So a here is 2 and r is 1/5. If you check r equals negative 1/5, you'll see you're going to run into a problem. Because if we use the same equation here, 2, a into 1 plus r equals 12, well, it'll be a into 1 minus 1/5 equals 12. And 1 minus 1/5 is 4/5 equals 12. And to get rid of the 4/5, I first multiply by 5, then divide by 4. 4 goes into 12 3 times, and you're left with 15. So in this sequence, it's going to be 15 times the negative 1/5 is going to give you, so 15 divided by 5 is 3, but negative, so negative 3. Times by negative 1/5 again, it's going to give you positive 3/5. Times by negative 1/5 again, negative 3/25. So first of all, even though the sum of the first two terms is 12, 15 minus 3, it breaks down because all the terms are not positive. There's now negative terms alternating in this sequence. So although there were two possible values for r, and also both did meet the convergence criteria, the fact that we were told that they had all positive terms was the differentiating factor here to finding the correct r value. So if I do my sum to infinity, a over 1 minus r, so a was 2 minus r, which was 1/5. So, sorry, a was not 2, a was 10. I'm looking at this thing here. I don't know why I said a is 2 there. That should be a equals 10 rather. So it'll be 10 over 1 minus 1/5 is 4/5. And when you divide by that fraction, you multiply by the reciprocal. Right? 10 times 5 is 50 over 4. And 2 can go into there twice. 2 can go into 50 25 times. So I do get 25 over 2 as the infinite sum. Okay, so the a value and the r value that I worked out, a equals 10 and r equals 1/5, those two values do satisfy all those properties. The geometric sequence has only positive terms. It does have a convergent infinite sum of 25 over 2, and the sum of the first two terms is 12. Okay, and that is solving this problem. I'll see you in the next one.